Suppose that an object has an amount of gravitational energy that equals the object's weight times its height above the ground, and that it has an amount of kinetic energy, which is the energy of its motion, that equals 1/2 times mass times speed squared. Is it correct to say that free fall in the absence of air resistance could be described as an object losing gravitational energy and gaining a corresponding amount of kinetic energy? So, okay, that's a pretty long-winded question there, but I want to put that into a picture. We're thinking about an object in free fall, and I'm going to start that object right here. Let's say it was maybe released from rest, some height above some other spot that I'm just going to say represents the zero for height. Maybe that's where it lands and hits the ground, but I don't want us to get too focused on it hitting something because that's actually not part of the process that I'm describing right here. But what I would like to say is, okay, we're talking about an object that started at a height, and I'm going to actually describe this as a height h here above some other spot. And in that sense, I'm going to say, you know what, this first spot, I'm going to think of that as the initial state for this system. And in that sense, reading through here, like we got initial state, let me also put final state here, but if we read through, I'd like to associate some energies with this initial and final state. And then the question it's asking us is this correct to say that free fall would be described by this in the absence of air resistance? Well, I don't know, right? How do we decide if something is correct, right? Well, okay, initially, I think it has gravitational energy, right? And it says that gravitational energy, so I'm just going to say here initial energy, and I've identified that that is gravitational. But it says here equals the object's weight times its height above the ground. Well, weight is equal to mass times free fall acceleration, in other words, mg, and then times height above the ground. And, you know, whether this is ground or not, I'm just going to assume that that's my ground reference there. So I'm going to use that same h I described right there and say, okay, that's the initial energy, right? That's I think, a good interpretation here. But then it says, okay, what's going to happen in the final state? Well, if in the final state it's reached h is equal to 0, effectively it's fallen through that h. And at this point, of course, it's moving with some, maybe I should throw into the picture here, it has accelerated, and then now it's moving with some downward speed v, right? So what kind of energy would it have there? So I'm going to write like something for its final energy. And it says in the problem statement that, you know, kinetic energy, the energy of motion, equals 1/2 mass times speed squared. So that formula would be 1/2 mass times, and speed, we'll use v again. So speed squared, 1/2 mv squared is the kinetic energy formula. Both of these formulas, by the way, are going to be tools that are going to be in our sort of box of tools for doing energy problems. But again, the question is saying, is it correct to say all this about free fall? Well, how do you know? Well, the way that we're going to look at this is we're going to make the claim that these two formulas represent all the energies that are there for this process. So they're all there is to keeping score in that sense. And if there is no energy added to the system or energy lost to the outside, I could maybe make the claim that the initial energy should equal the final energy. And it turns out, as we go on, we see that there are some kinds of problems where you won't be able to make this claim, usually because there is maybe some energy lost to something external to the system in some way. But if you're confident that it's not, then you can say this. And even though I don't really know what I'm doing yet in this topic, maybe it's okay if we say this. And then, so if we want to determine if it's something correct, well, how do we do that, right? Well, I don't know. Let's go ahead and write mgh is equal to 1/2 mv squared. I mean, I just said I don't know how to determine if something is correct, but let's do some math. Maybe that's a way of determining if something is correct, right? So I can knock off the masses there because they're on both sides of this equation. And, okay, that's rather interesting. So I would have GH is equal to 1/2 V squared. What if I went ahead and multiplied by 2 on both sides and maybe rewrote things in terms of V squared is equal to 2 GH, right? Well, if I looked at this system a little bit differently and I said, okay, V naught is equal to 0, and of course V final is equal to just V, and if I recognize that acceleration was equal to G, and that the total displacement of the system was equal to h, right? And if I had written the fourth kinematic formula, v squared is equal to v naught squared plus 2 A delta x. And then I made all the appropriate replacements. This one goes to 0. A becomes G. Delta x becomes H. And I get the same result. So in other words, if I'm getting the same result and we know this one is correct, I think I can say this result is correct. The thing that energy did is it just gave us a different way of telling the story for getting there. So let's check that with the answers. See what it says. And it's talking about initially there being gravitational energy, mgh. And it talks about here like right before it hits the ground. So that's one way. I mean, I kind of sidestepped the concept of like, well, is this the ground? Did it smack there? Because I didn't want to include the collision with the ground as part of the process. So that's why it said here, right before it hits the ground, the object is falling with a velocity v and has kinetic energy 1/2 mv squared. The two energy formulas we use, though, are right there in the language. And then it says if all the gravitational energy becomes kinetic, that means mgh is equal to 1/2 mv squared. That's pretty much what we argued. And at the end, we got that. And then what we've done here is show, well, we already know that that was a correct result.